So we're going to pick up from where we left off in three-dimensional space. So this is our picture, which shows 1 point, x, y, and z, and it gives the coordinate along the x, along the y, and along the z. So just as a reminder, if we have the vector AB, then we take so if we have the vector AB, we can take the tip and subtract the tail coordinates for the position vector. Then if we want to actually find the magnitude, then again we're using this distance formula now that we actually have the vector, and because we've already done our x2 minus x1 squared plus y2 minus y1 squared, and so on. And then remember, this has to be a positive number. So some properties with vectors are very similar to what we see with real numbers. So this is just showing you that we can use properties the same way as we do in real numbers. So if we have x plus a is equal to b, we can subtract a from each side if we want to isolate x. If we have a number multiplied in front of x, then we can divide both sides by by k. So let's look at our first example. So it says solve for x. So I'm just going to use my properties. I have 3x minus r is equal to s. So I can add r. 3x is equal to s plus r. And then when I divide by 3, what I'm really going to do is I'm going to write it as 1/3 s plus r. So basically I have the vector s plus r, but it's only going to be 1/3 of that in magnitude, rather than dividing each one by 3. For b, then I'm going to get x by itself. I'm going to do c minus d is equal to 2x, and x is 1/2 of c minus d. So because c and d are vectors, we're really going to subtract them and then take half of that overall magnitude. For this question, I'm first going to rewrite. I can pull that 2 out in front, so then I can isolate a and just find the magnitude of a using my distance formula. So -1, that's my x component. 3, which is my y component, and 2. So 1 plus 9 plus 4, which is equal to 2 square root of 14. So for this question, I need to find coordinates c and d. I'm given a and b, so I'm going to start with finding my vector for a and b, because that is information that I can use right away. So if this is the tip and this is the tail, then I'm going to do tip minus tail. So for my vector, I will get -1 minus -2. So -1 minus -2, -2 minus -5, and 2 minus 3. When I simplify that, I get 1, 3, and -1. Now let's say that we have this origin right about here. And remember that this is 0, 0, 0. So if I want to find d, let's say, then really what I'm trying to find is origin d. Just like this coordinate a is equivalent, so a is equivalent to origin a, and b is equivalent to origin b. So if we're going to find origin d, so let me just do like a little, this is really what we're trying to find. Well, how do we get there? We can't just figure out from origin to D, but we can say if we take A and we add it to AD, then it will result in origin D. So really, I'm saying origin D is the same as origin A plus AD. So what is origin A? Origin A is just our A value. So I'm going to put the coordinate A, so -2, but I'm going to write it as a vector, -5 and 3. Now what is AD? If we look at our graph, AD, it looks like these are pretty evenly spaced. So from here to here is 1 unit, here is 2, and here is 3. So between A and B is an equivalent distance as between B and C and between C and D. So we can actually say that AD is equivalent to 3 times AB. So AD is plus 3 So what is 3AB? Well, we already found AB, so plus 3 times vector 1, 3, -1, -2, -5, and 3. Plus, so 3, 9, and -3. If we add those together, we get 1, 4, and 0, which is vector, whoops, not A, vector D. Now let's do the same thing for C. So again, we're trying to find from the origin to C. Well, we can say that that's the same as the origin to A plus 2 times the distance AB. So if we go back and look, we're saying here, whoops, it's kind of hard to see. From here to here is A, and then we want to know if we add this, AC, that will give us C. So we get -2, -5, and 3, plus 2 times 1, 3, and -1, -2, -5, and 3, plus 2, 6, and -2. We add the x components, we get 0. We add the y components, we get 1. We add the z components, and we get 1. And that is C. We like to be able to reduce things to what we call a unit vector, which means that the vector actually has a length of 1. So in two-dimensional space, these are represented by the letters I and J. So I along the x direction and J along the y direction. In three-dimensional space, we call them I, J, and K. So notice that for the x direction, the 1 is in the x component spot, the 1 here is in the y component spot, and the 1 is in the z component spot. So if we're given this question, it says find the length of a 2D vector, which is 2i minus 5j. This is just a fancy way of saying our x component is 2 and our y component is -5. If we're going to find the length, we're going to use our formula. So 2 squared plus -5 squared, which is the square root of 29. So really, they're just giving us the same information, but in a little bit different form. So for this one, it's asking us to find K. It's giving us our horizontal and vertical component, and it's telling us specifically that it is a unit vector. So that means that we know that the length is equal to 1. Well, our length formula is square root of -1 over 3 squared plus k squared, and we know that that's equal to 1. So we can square both sides. Then if I simplify inside, I get 1 over 9 plus k squared is equal to 1. We subtract 1 over 9 from each side. So k squared is equal to 8 over 9. And then we take the plus or minus square root. So k is equal to plus or minus 2 root 2 over 3. Now, if we take the unit vector one step further, remember the unit vector meant that the length was equal to 1 unit. But we know that vectors also talk about direction. So this is our formula. It is 1 over the magnitude of the vector times the vector. So for example, if we have vector b and it has some length of k, and we know that it's in the same direction as another vector, then we would say b is equivalent to k over the absolute value of a times a. If a vector b in length is parallel, so that means that it has the same magnitude, but it could be going in the other direction, then the only difference here is that it could be plus or minus, because remember that's telling you direction. So how is this used? Here's our example. Find vector b of length 7, so that's our k, the opposite direction, so we would need to use a negative, to the vector a is equal to 2, -1, 1. So if we use our formula, we say b is equal to negative k over the absolute value of a, or magnitude a, times a. So we simplify, -7 over, we have to find the magnitude, so 2 squared plus -1 squared plus 1 squared. And then we're going to multiply it by the vector, 2, -1, 1. So we simplify that to be -7 over the square root of 4 plus 1 plus 1 to -1, 1, which is equal to -7 over root 6 to -1, 1. So really we just have a multiplier in front of our vector, and this is actually your final answer. And it doesn't look like they're asking you to rationalize the denominator here.